Hello and welcome to today's Saratech enablement session. My name is Andrea Hall and I am the Customer Relationship Manager here at Saratech, and I will be your host today. Presenting, we have Daniel Nadeau, who is an Applications Engineer here at Saratech, and he'll be talking to you about topology optimization in Simcenter. Our sessions run about 30 minutes each, and they are all recorded and posted to our Saratech YouTube channel. Make sure you check out our past sessions there. Twice a month, we meet here to learn about tips, tricks, new and old features that will help you in your everyday tasks. This is an open forum, so if you have any questions or comments during the presentation, please type them into the chat box and I will kindly interrupt Dan and let him know about your comments and questions. And with that, I will pass the baton over to Dan. Thank you.
Thank you for the introduction. Hello and welcome. My name is Dan Nadeau. I'm an application engineer for Saratech. My expertise include FEMAP, NX-CAE, NX-CAD, and NX-Nastran. So today I'm going to talk about topology optimization. So here's a brief definition from Wikipedia. Topology optimization is a mathematical method that optimizes material layout within a given design space for a given set of loads, boundary conditions, and constraints with the goal of maximizing the performance of the system. So my plan today is just give you a brief overview of optimization inside NX, and I'm going to give you a demonstration then using Simcenter and NX12. So in the release of NX12, there are two types of topology inside NX. They call it designers and they call it analysts. So one is inside the CAD environment and one is inside the CAE environment. So I wanted to discuss both of them and I guess show you some pros and some reasons why to use one over the other. They both do a great job. It's just, up to you to determine which one fits your needs. So I'm going to go through both of these as well. I'm going to spend most of my time doing the CAE one. We're going to have a webinar coming up where we're going to go through some of this in the CAD environment as well. So here is our optimization using Nastran Solution 200. So this would be inside the Simcenter. So here's just a basic workflow. So we have our CAD part. We're going to build our finite element model. We're going to set it up for a Solution 200, which would be topology optimization. We're going to specify our areas that are design areas and our frozen areas. We're going to specify some sort of objective. With this objective, we're going to specify some sort of constraints, which could be manufacturing constraints, other constraints, displacement constraints, frequency constraints, etc. We're going to specify solution parameters. We're going to check our study and look at our results. So from our results, we're going to verification, are these what we want? And then from there, we're going to get new output geometry, and then we're going to do further design work based on these results. So one thing that's important with topology, this isn't your final design. This is the introduction to your design to make sure that it is optimized. So a lot of times you'll get your results, and then from there, you want to make changes and continue down your design path. So at the bottom, I have a simple optimization example. So we want to maximize stiffness of the structure while keeping the design mass between some sort of boundaries. And we also want the flexible mode to be above a specified frequency. So you can see we have our objective and then we have our constraints. So that is the basic for our topology optimization in Solution 200. So inside Simcenter, there's only one optimization objective. So in this case, it could be compliance or model weight. So with these two response types, you can specify if you want to minimize or maximize them. So a lot of times you want to minimize your compliance, and you want to minimize your weight in a structure, or you want to specify something based on compliance. So do you want it to stay stiffness, or do you want to worry about the weight of the structure? So only one of these can be used in one given solution. The next thing that you need to define is the design area. So the design area is the location that you are going to remove elements in this case. You can specify two different types of the design area. One can be optimization area. the area where you're going to remove entities, and then you can specify frozen areas, which is areas where it will ignore. You do not need to specify both. Sometimes it's easier just to define the frozen area, and then it will use the remaining areas for optimization. The next thing that you need to define is a design constraint. So you need to define your responses based on something such as weight, your design area weight, or sometimes normal modes would be one. There are other design constraints we can define. They're called advanced constraints. I'll talk about them in a second. But we can define these constraints at a global and or a subcase level. So if you want to do this at a global level or within a certain subcase, so maybe you want to run a bunch of subcases, modes, statics, frequency response, etc. You can specify those at a subcase level. So here are some of the advanced design constraints that we can define, and you see that we have a large list. So instead of our simple ones as the weight and the area and the modes, now we have things like stress, strain, deflection, and we even have some dynamic constraints that you can specify as well. The next thing that you need to define is your manufacturing constraints. Depending on your manufacturing constraint, you will get a completely different result. So it makes sense to understand these type of manufacturing constraints based on how the part is manufactured. So if you are doing additive manufacturing, it might make sense to use that as a constraint type. If you are doing, like you've seen in this picture right here, cyclic symmetry, you could do that. In my case, I'm going to do planar symmetry because I want the part to be symmetric about a plane. So after you specify all your parameters, now we go to our optimization parameters. So this is at our solution level. So this is where we go ahead and we control our convergence and output, and you can even change your calculation method using this penalty law, DMR law variable. So in our case, we want to specify a certain number of cycles. In this image right here, they're specifying 20 cycles, and they want output at the initial and best. If you are doing this, I recommend doing a lot more than 20 design cycles. I've noticed while running these solutions, you want to make sure that you have a decent amount of design cycles. I was getting good results when I put at least 50 design cycles. It will take a little bit longer, but then it gives a lot more iterations. And I like to change my recovery options to initial and all improved so that you get to see the results as it goes through every one of those design cycles that you specify. Now, after you solve your solution, you get output. So from here, the results, what we can do with our results is we can get out an STL file, and we can also get out an Astran BDF file. So these are important informations that you can use to continue to design. So maybe you want to make changes to the leftover elements, or you want to use the geometry based on the STL file to make changes to your other, your original geometry. You can compare it to the STL file and make changes, to continue to design. So one of the outputs that you get is this normalized mass density. So it tells you in a plot material that you can keep or remove based on your analysis that you solved. There is also a button to create a verification solution. So this takes all the elements that retained or was left based on your solve or your solution, and then it lets you run a simple case to see if your stresses, strains, and your results based on the elements that it wanted to keep. What I recommend doing is export out the BDF, clean up the BDF a little bit, and then rerun it to do your own verification solution, but both are fine. So that's the steps to go ahead and use the Simcenter topology optimization tool. The next one is topology optimization for designers. It's embedded in the CAD environment. You'll notice up here, this is the toolbar that is used to do topology optimization in NX. You'll see it is pretty straightforward. It's not as complicated, if you will. So it focuses on the functional requirements of the design. You get fast results, and you get highly smooth convergent models that you can use for additive manufacturing, printing, or for help for a redesign. So here's the workflow if you are using this type of topology. So you see now we manage bodies. You specify the bodies that you want to use in your solution. And inside your managed bodies, you specify how these things are connected together. So you have multiple bodies. How are they connected together? If you have design constraints, loads constraints. If you have scenery bodies, things that you don't want the optimizer to work, you specify your areas where you want the design optimization to work, specify areas to keep in, keep out, etc. You would do in your managed bodies. So after you get your body all set up, you specify your material. If you have global loads, accelerations, type like that, then we set up and we run our optimization, and then we can go ahead and look at our results. Now, the important thing when you're doing this is to understand the design space. So the design space is the envelope that the optimizer uses. So when you are doing optimization, you want to remove areas to set it up as a big region for this design space to use. So in your original model, you don't want to make it all detailed. You want it as little, fidelity as you can. So you want the thing to be really nice and open so that you can take parts out and use all that design space. So with this, you get results. So you get new geometry, displacements, and stresses. So that's just a brief overview of the difference between these two topology optimizations. So I'm going to hop into NX and go over some of them. So here is a simple part in NX. So here we'll just look at it, and you'll see that there's some cutouts, things like that. It's been shelled. Now for our topology optimization, we don't want these regions shelled out. We want the optimizer to see this large design region. So we would make some changes in the CAD to go ahead and set that up. So that's what I went ahead and did in one of these other models that are open. So I just took that same model and I just gave myself this large design space. Now that I have this large design space, I can go ahead and set it up to be optimized. So the first thing that I'm going to do is I'm going to take this guy and I'm going to bring it into Simcenter or Advanced Sim. So to do that, we can hit Applications, Pre-Post. And now that we are in Simcenter or Pre-Post, let's go ahead and create our new Fem and Sim. So new Fem and Sim. I'm going to create the idealized part. In this case, I'm not going to use it, but in case I need to ever go back, I can change this idealized part. I won't mess with this part right here. So in this case, I'm going to set it as a static solution. It's a good idea to run a linear static solution to begin with, and most likely run a normal mode solution. Let you know where you're starting with, and then you can go from there. So now that I have my model brought in, set up, I have my Fem part, which I'm working on right now. Let's go ahead and mesh this. Now, since this was created in a CAD environment, I'm not too sure mesh mating conditions were created between these two faces. So let's go ahead and specify mesh mating conditions. If I would have cut this at the idealized part, I would have specified mesh mating conditions, but since it was done outside of Simcenter, let's go ahead and specify mesh mating conditions. So what this does is, now that these are separate bodies across this region, when I go ahead and mesh it, I'm going to have nodes that align with each other. So it helps me in my meshings. So let's go ahead and throw a mesh. So I'm going to put a mesh collector, and I'm going to give it a name. And then I'm going to go ahead and define the solid property. And in this case, I'm going to define a material, and I'm going to use my library materials that exist. If I had to type my own material, I could create my own material, but in this case, I'm just going to use 6061 aluminum. So now I have my property. Let's go ahead and throw a mesh on there and reference that property. So I'm just going to highlight the part. I'm going to use this little calculate element size, and then I usually go around half that, maybe sometimes a little bit less to get a nice mesh on the part. Now, if I wanted to change some of my mesh options, I could go ahead and do that here. You see it's going in the collector that I specified. Now, if it will automatically create a collector, so you don't need to create a collector. I like to create them ahead of time. It's just my order of operation, how I like to go about it. So now I'm going to go ahead and mesh the part. All right, as you can see, the part has been meshed. To help my visualization, let's go ahead and change some of these colors. I'm going to go ahead and find this center section. Yep, and let's go ahead and edit the display, and let's change this mesh to be blue. Just helps me visualize the difference. And in this case, I want to use the blue area as my design space. So let's see if we can remove some material and get good quality results here. All right, one other check that I like to do here is let's do a duplicate node check. Let's just run through this just in case. I know I did mesh mating conditions, but you never know. No duplicate nodes, so model's good. I recommend running some more checks in this case, but we don't have too much time, so I'm trying to get it all in. All right, so now I have my finite element model set up. Let's go ahead and go to the sim part. And at the sim part, let's go ahead and put some loads and constraints on this. So I'm going to go ahead and put a fixed translation constraint at the bottom. So I'm going to right click down here on constraint container, create a new constraint, fixed translation. You can always do it from the pull downs as well. I prefer the right click method. Yes.
Sorry to interrupt. Christine was wondering if you could change the color again.
Yeah, sure. So I'm going to apply these constraints real quick. So all you have to do is at the FEM level, if you go to the collector, you specify your mesh, and I'll just grab the other ones. And you just right click, and you can say edit display, and then right here is color. You can change the width as well, and you have some other options. So instead of green, give them red. And now if I hit OK, now those have become red. I apparently changed this one. Okay.
Thanks.
Yep. So it's just this display. When you write, my recommendation is right click on the level, and then right there, a lot of these have edit display, and then from there you can edit display of a lot of the entities in the tree. Okay. So I'll hop back up to my sim part. I have it constrained in this direction. So let's go ahead and apply a load to the structure. As you can see, I didn't change the color at this level. I changed it at the FEM part, so that's why it's different here. So now I'm going to go ahead and right click on loads, say new load, and I'm going to apply a force. And I'm going to apply a force to all these, I'll say pin locations at the top. Now I could create a group and make this easier, but I only have force selection, so it's not too bad. Now in this case, I want to apply a load in the negative X direction. So I'm going to symbolize somebody getting up and yanking on the seat in front of them to pull this thing back. So if you would think this would be right up below the handrest on like an airplane. So this would be the bracket that would, connect at the bottom, and this would divide the passengers. So we're just symbolizing somebody's pulling back on it, and I'm going to specify my vector in minus x sum c, and I'm going to enter in a value of 5 kilonewtons. So there I have my force of 5,000 newtons. I could have put e to the 3, apply. And now I'm going to apply it to the same location, but I'm going to symbolize somebody, I guess, getting up as well and pushing down on this entity. And this time my force is going to go in my negative z direction. And I'm going to specify a value of 11,000 newtons. Now, for instance, maybe you didn't know the value in newtons, or maybe you wanted to specify it in a different unit system. You could specify whatever you wanted here. So this is the one nice thing is with the units, maybe if I knew this value in pound force, so it's about 2,400 pound force. So I could enter it in like that. And those are, inconsistent units, but at least I have the same values as well. So that is not a problem inside Simcenter to do that, like in that type of solution. So now I have my entity set up. I have constraints, loads. I can go ahead and solve this model and look at our basic solution. So in my case, let's go ahead and solve it really quick. So it's sending the analysis in Astro, and this should take a couple minutes. So what we're going to do next is we're going to go ahead and set this up for optimization. So we're going to minimize weight of the structure. So a nice thing to check real quick is what is the weight of the structure. This is always a smart thing. So I could say checks, and let's go ahead and give it a solid property check. And I'm going to go ahead and check the solid properties of the structure. So I'm going to grab all these elements, hit OK, and it's going to list it in a table for me. So I can see right now my structure is about, what, 5.5 kilograms, give or take. So when we go ahead and optimize it, now we know where we're starting at. And I'm going to go ahead and write it down so I don't forget. So this solution should be all but complete. We're just running a static solution because maybe we want to use some of this information for our next solution. All right, so now I have results. I can go ahead and post-process them, look at what we have. Maybe we're interested in displacement in the X direction. So when somebody, yanks back on that, is it going to, how far is the seat going to move? Is it going to hit it? Maybe there's some sort of regulation. So we can change our contour plot, hide some of these elements, make it easier to see what we have. Maybe we're interested in all this design space and we want to look at it, put annotations and see, oh, well, this location right here has a maximum of 0.35 millimeters. But maybe my regulation is, oh, this thing can actually move 3/4 of a millimeter before something happens. So maybe when I go ahead and optimize it, I'll say, hey, you can move, all the way out here, and that's fine. You still meet my design criteria. So that's one of the nice things that you can do with optimization. So we're not going to use any of the information here. I just think it's smart to look at our baseline, see what we have, and then let's go and optimize it. So now that we have this set up, let's go ahead and create a new solution. So you can go back to our tab and hit new solution. You can also right click down here, whatever you prefer. And this time we're going to go ahead and specify solution 200 topology optimization. And I'm going to accept the defaults now, and we'll get back to there in a second. Now in this solution, let's go ahead and grab those loads and constraints that we specified earlier. So now I have my loads and constraints defined. Now we have to go ahead and specify the other entities. So our design objective. So let's right click on our design objective. And what we want to do in our case is we want to minimize compliance. So we specify our design objective. Remember, we're only allowed one per solution here. Now let's specify our design area. Let me go ahead and unfringe plot that. There we go. So specify my design area. So I want to specify the optimization area. So I'll give it a name, optimization. Here's the optimization area, and I'll just give it a label as 1. And now the optimizer will know this as area that can be optimized. Now you do not have to do this, but I like to do it just in case, and it helps me understand what I'm doing as well, is you can specify the frozen area. So these are the areas where the optimizer is not going to use. To me, I like to define both, but maybe you have a large structure and it's easier to define one or the other. That might help. So for my case, it's pretty straightforward to define both. And it just helps me visualize that I specified the correct things as well. Next thing that we want to do is define a design constraint. So let's go ahead and right click on design constraint, new design constraint. And in this one, if you remember when we looked at our mass, it was a little over 5.5 kilograms. Maybe regulation or some sort of parameter saying, hey, let's get this thing down to around 2 kilograms if we can, and let's go max, we'll say 2.5. So we're trying to go a little less than half of the weight of the structure to begin with. So this is a decent amount of change to get there. So one thing that is important when you are doing these, you can't put some lower limit of like 0.0001 kilo. It has to be a reasonable value. So it's nice to give it a value which it could achieve. So now I have my constraint, and I'm going to define a manufacturing constraint. And this time I'm going to say planar symmetry. So I'm going to grab something on this plane. For me, I'm going to grab, I guess, a node right here, this curve. And I can just say midpoint. I'll grab the midpoint, and I'll specify the symmetry in this Y direction, which is this way. So it's symmetric about the center of the structure. So when I get results, it'll be symmetric about that structure. So understanding the manufacturing constraints is pretty powerful. Now, one other thing that we could do down here at our subcase level, maybe we wanted to add an advanced design constraint or another design constraint, and we want to say, oh, let's say the displacement of, I'm just going to pick a random node. This node can't be greater than, here's my lower limit, and it can't move more than, 3/4 of a millimeter. So if I wanted to specify more design constraints, I could specify them. Or maybe I wanted to do an advanced design constraint. And inside here, I'd say, oh, well, instead of this, I want to say the stress of, the solid property. I'm going too fast, I'm sorry. So you could say the stress of some sort of property, and I want to limit that to be less than some sort of MPa. So if you add on more and more of these responses, it's going to take longer to solve, but you will get good quality results, and it will based on these responses that you specified. So now that I have my model set up, I'm going to go ahead and solve it. Now this takes a decent amount of time. So one thing that I would do is go to my solution, make sure it's the active one, and I would say, oh, I want to give it 60 cycles, and I want output at initial and all improved, so I get output at every time it went through it. Now, after you would set this up, if you need to change any other parameters, maybe you wanted to use a different optimizer, you could change that. So I went ahead and solved it on another screen just because it takes a decent amount of time. So now we'll just say I solved it. Now I have my optimization results. We can go ahead and look at it. So it'll give you, and I ran 50 design cycles. You can look at the static results, and you can also look at this thing called the normalized mass density. So it's a good way to visualize the load path. So I can see after my 15th design cycle, it thinks this is going to be the load path of the structure. And now I can go ahead and look at my last one. So I'm going to look at my material density results, but I'm going to look at for my 50th case. And it thinks this would be the optimization of the structure. And if I zoom in, you see it bored some holes out of there. But maybe I didn't want that to happen. I would have to enter in some more design constraints to make sure that this would be a solid part. So for my instance, I probably wouldn't want this, but I would have to try a different design constraint. You can look at from your results. So it's giving me what elements it thinks it should keep based on this model. So this is a great way to go ahead and start your design. You can look at this. Right from here, you can go ahead and export this out as an STL file, and you could map this on the original part, and then you could go into CAD and cut out these regions and re-bring it into FEA and solve it again and look at your results. The other thing that you can do is export this out as a verification solution. And what that does is it creates a new solution for you. And I already did this. And it just has all the elements in the model. So it creates a new solution that you can solve linear statics or modes or whatever you solved in the original and look at stresses and strains. So that's a nice little verification. What I recommend doing is getting your BDF file as you export out here as a BDF. So right here you can hit export and export out, and then just clean it up a little bit because you have some erroneous elements that might not be needed for that solution, and just get a nice quality model as you would think to go ahead and solve it. So that's the optimization in Simcenter. I know I went through it pretty fast, but I want to make sure I can spend at least 10 minutes or so on the designer optimization as well. So I'm going to go ahead and pop over here into my next one, which would be using the topology optimization in NX. So you can see I changed my design even more. So I have this whole region to use optimizer on. Now, in this one, it is a tab inside NX, not in Simcenter, and it's a topology optimization. It is a separate installation. So the first thing that I do is I'll assign materials. So select the entity. And this entity, just like I did before, is 6061 aluminum. And now I need to manage bodies. Now I only have one body, but imagine if you had multiple, bodies setting this up. You would have to then do a connection from one body to the other. In mine, I only have one body, so I'll grab the body. I'm going to add it to the list, and this thing is going to be design space. So I'm going to say, oh, we're going to use this material, and we're going to use this as design space. So inside here, we'll manage our design constraints. So in this one, I'm going to say, oh, give me, we'll say void fill. So in this, it wants to exclude voids. You know, in this case, maybe I don't want holes in it. Or maybe I want to use planar symmetry like before. Just grab it, specify a plane. You'll see I'm in the CAD environment now, so it's easier to grab some of these entities. I'm gonna grab the midplane. There we go. And now I have, you know, no holes, be symmetric about this location. So that might be a good design constraint. We'll specify our optimization features. So in this one, I'm gonna go ahead and auto-recognize features. And these features are auto-recognized from the model history. So if it's created in NX, it's really nice. So here's my first hole right here. I'm gonna go ahead and say, oh, well, I want you to keep out of this, and I want to keep out 24 millimeters. So that gives me a nice round area, and I'm cutting out that region that I didn't want to use in the other one. And then I don't want a constraint here, so that's good. The next one is down here. Well, this one I'll fix it. I could do a slider as well. And I also want to keep out 24 millimeters. The next one is up here. I don't want to constrain it because I'm going to load it. I'm going to apply an offset of 24 as well. Then the last one, I want to constrain it, just like the other one I have those regions. So what I said is, hey, let's constrain these guys, and all 4 of these holes give me 24 millimeters around it to keep out. So the optimizer ignore. Next thing, I'm going to manage my load cases. And you see it has all the features already defined. So I'm going to say this hole, hey, give me a force of 3780 newtons. So I sort of simplified my other model, and I'm going to specify a vector as like this edge. So instead of modeling them as a left and say a cross and a down load, I'm just doing it at the 45. So now I have that load. And then the other entity, I'm going to load again with that same value of 3780 newtons. And I'm going to specify that same vector to apply the load. I guess I put it backwards, so I'll go ahead and flip that around. Specify the vector, and let's flip it around. There we go. So now I have my loads and constraints set on the model. So that is the basic setup. We specify our design constraints, our features we want to optimize, and our load cases. If we have any global loads, we can define them here. And then we go ahead and we hit Setup Optimization. So inside here, our only optimization type is to minimize strain energy, subject to a target mass. So I like to hit Estimate. It will give me a value. And this gives me a minimum and approximate mass of all the design space. In our other model, we set about 2 kilograms. And then you would go ahead and specify right here a global resolution. This will give you a mesh. So you notice this model has no mesh in it. It's doing the mesh in the background right here by specifying a size. So you specify a decent size, figuring out how you'll get an output. It will take longer if you do a finer mesh. And then you just go ahead and run optimization. Now I have already ran this solution, so I can go ahead and open one. So here is a structure that came out of it. And this one, I just did a planar symmetry constraint, and you can see it's nice and symmetric throughout the middle. I don't know how well it comes out, but I got this nice model that's in this nice CAD form. It's got this region that I specified around all these holes to be a keep out. And from here, you can look at displacements, and you'll see that it's just a simple scale, 0 to 1. You can't really interrogate this too well. And you can look at stresses, which is von Mises stress, and you get some output. And then if you wanted to convert this to a facet body, you can convert it to a facet body and use some of your reverse engineering tools for additive manufacturing or whatever you're doing with this part then. Now, one important thing when you are using this is you can get all sorts of different results. I did this little example of, I specified different design constraints. So I said, hey, give me one with more lattice type structures. Give me one that didn't give me any holes. So for this instance, maybe you didn't want things to be falling between the seats. Maybe you want no fills, and it just hollows it out, and it gives you that region. But you can tell each one of these structures is still following the same sort of load path. So they all have the same load path. So it's important to understand the load paths and use that as the design. So realize this isn't your final design, but it's a good way to start. All right, so I know I went through some stuff pretty fast, and if you guys do have any questions, please reach out. I wanted to make sure I covered a decent amount of content. So I'm gonna go ahead and hop to my summary. So at this point, I showed you topology optimization using NX and Simcenter. Now, I guess the question comes up a lot is which solution is correct for you? If this is of use and you think this would help your design, I think it's very powerful. So the answers could be designer topology optimization or analyst topology optimizations. Now, here's some things about them. So for the designer topology optimization, it's based, more for a CAD user. It was easy to use. Hopefully I showed that it was much easier to use. It's faster. I didn't need to know, Simcenter to do it. I could work everything in the CAD, the CAD platform. I didn't need to know, high-end FEA knowledge. I just need to know the constraints and loads. I get really nice, smooth geometry results. It's easy to convert into a convergent model. So maybe you're using convergent modeling after that. And if that's what you're doing, you're already in the CAD environment. So there's some greatness in there. If you are using the analyst topology, you are a Simcenter user. You have extensive FEA knowledge. You have access to all the FEA modeling tools. You have more response types, frequency, displacement, stresses. We didn't have all those in the designer topology optimization. It uses the Nastran solver, solution 200. So maybe, requirement makes you have to use some sort of solution like that. You get all the post-processing information. So maybe you need to interrogate a little bit more. You have more boundary conditions, loads, constraints, maybe pressures, etc. So you have all those FEA things that you can add. Now, I won't say one's better than the other. I will tell you that, to do the analyst topology optimization, it's a lot more, work. You have to understand the FEA stuff besides the topology thing. So I hope I showed both of these technologies on topology optimization using NX12. And if anybody has any questions, please feel free to reach out. Thank you.
Great job, Dan. Thank you so much. I know you had a lot to present in a very short amount of time. Usually the feedback that we get on these sessions is people wish that they were a little longer, and we try to keep it quick and short so that people can attend during work hours and during a lunch break, things like that. So if you guys have questions, I know Christine had one more question, Dan, so I'll have you follow up with her after the session since we're kind of running low on time here. Our next session will be on March 15th, and Mimi Lan is going to be talking about Simcenter motion topology optimization for additive. So that is something that you guys will definitely want to see. We will be here again 11 a.m. Pacific, 2 p.m. Eastern. And like I said, we always post these to YouTube, and we also send out the link after the session is over. So if you don't think you're going to be able to make it to the session on the 15th, go ahead and register for it, and we will still send the link out to you as soon as it is ready. Next slide. So Saratech, some of you are customers and some of you are just people kind of popping in to see what this is all about. So I wanted to make sure that everyone is aware that we also do engineering services that address your demand for advanced engineering capabilities. Reach out to us if there's anything we can help you with when it comes to services and additive manufacturing. We have some really awesome machines, Mark Forged in HP. We've been working with them for a while, and we have some engineers that are very well versed in those. So if you have any questions or just curious about 3D printing, please make sure that you reach out to us. The easiest way to get us is info@saratech.com. That's a good way to get us quickly if you have any questions about that kind of stuff, and we can go ahead and pass it along to the right departments. Next. Make sure you follow us on all of our social media accounts, especially YouTube. That's where you will get notifications about our sessions that are posted, and we're going to start posting a lot more kind of shorter videos as well. So you don't want to miss those. So make sure that you subscribe to all of these, and that way you can see those firsthand. And then if you don't mind, just stick around for about 30 seconds after we close out this session. We would love your feedback. Let us know how we did today, what we can do to improve. And if you have any questions, you can also put that in the survey, and we will follow up with you afterwards. Okay? Thank you so much for attending, for taking the time to be here, and we hope you have a wonderful day.